All right, and like I mentioned today, this is going to be actually our first section in Module 3, so Section 17, right? We're going to introduce like probability, which is going to lead great into the rest of the module, which we're going to focus on statistics. Probability will basically allow us to build a whole lot of stuff into like distributions, and that will lead us a lot into statistics itself. So I think the rest of this week, if I recall right, it's going to be mostly focused on not statistics, probability and distributions. And I think in the following week, I'm actually looking a little bit aside. Oh, I guess we do at the end of this on section 20, we do start talking about hypothesis testing, which will lead us into statistical tests and statistics in particular for the rest of the module. Okay. So one thing I would kind of say, about probability. Probability is a really interesting thing for me, or like I always think it's really interesting, is that it's focused around the idea that probability represents things that you don't know. In a lot of ways, it's kind of like in a lot of, like, I don't know about you guys, but like depending on like how you view kind of like the universe, this is my physics side kind of popping out a little bit, but like depending how you feel about like how the universe works and stuff like that, you can either determine like, oh, things are deterministic in the sense that like, if this happens, this happens, this happens, and this happens. The problem is that there's just so many little moving parts that it's really difficult for us to know. But in theory, we could know all these little parts and actually, adjust. And that's actually, I think it's kind of funny. It's like when I was really little, I kind of like realized this at some point, like when I was like probably second grade, where I was just like, oh, like, it's like if everything is moved forward in this way, and I knew all these different parts, you could like tell the future. And that's essentially what science is, right? And essentially you're saying, oh, if you know these parts, then you know what the future is. Strangely enough, is that you can't know everything. And there's a lot of suggestions. I mean, everyone likes to go to quantum mechanics, like, oh, quantum mechanics, like is probabilistic. But even not considering quantum mechanics, has anyone heard of chaos theory before? Okay, I see a nod, see some head shakes. So it's actually mentioned a little bit in Jurassic Park, if anyone's read the novels. But chaos theory basically is a mathematical theory. And the whole idea of it, really summarizing, going through, is that when you have a lot of moving parts that can really like add up significantly, it's actually really difficult to predict anything, even knowing to really fine detail what these positions are. So for example, if you think about this like on like the moon, and like the planets stuff going around the earth, and or not going around the earth, going around well, I guess the moon's going around the earth, but going around the sun and everything, right? If you think about this, like we can predict like well into the future, like hundreds of years in the future, of like how these planets are going to be moving and where they're moving around and everything like that. Like that's a non-chaotic system, and for the most part we can pretty accurately like figure things out. However, if you ever notice about the weather, we get like 10-day forecasts. And why don't we have a month-long forecast or a year-long forecast, right, of like how the weather is? And the real reason why is because it's a chaotic system. There's just so many little moving parts that add up all together, right? So you can kind of think of that, like I think people probably have heard this like similar phrase. I'm going to probably get it wrong, like the original, but a butterfly flaps its wings in China and causes a tornado in like Texas, right? So like, and in a lot of ways, that's kind of true with weather, is that like every little aspect, like the fact that people are breathing, like there's a higher concentration of people, higher concentration of heat, like of just breathing in and out, can actually affect the weather. The problem is that there's so many little aspects, you can't do it. Kind of fun fact is like when supercomputers kind of became more and more, they thought like, scientists thought like, hey, we're going to finally be able to predict this weather. And it turned out, no, you can't. It's actually very difficult. I think I heard something, don't quote me on this since it's being accurate, but something our like 7-day forecast was accurate as like a 2-day forecast before supercomputers. And part of the reason why is because basically weather has such huge changes in like fluctuation. But that's where probability comes in, is that just because something's chaotic in the sense that we don't know for sure, we can say with probability, saying, well, there's a % chance of this happening. Or like, based on prior knowledge, we can say, well, this will happen. For example, flipping a coin, we say a coin has a 50-50 chance of landing heads or tails, right? So 50% of the time it lands on heads, 50% lands on tails. Why do we say this? Because that's like the classic mathematical example. For the most part, it's probably from experience, right? You kind of know, it's like, oh, it lands on tails. If you do actually test this out, I think it technically leans a little bit, American quarter at least, lands slightly on heads more often than tails, like very slight, like I think it's like less than 1%. difference. So, always choose heads, right? Um,
That's
you know,
really interesting.
yeah. And other things too is like 50-50 chance. There's actually a third option. I don't think most people ever really consider it, is if it lands on like its side. So like there's always like, you can see like statistics books talk about if it lands on its side, right? Again, this is me kind of diverging a little bit from like the curriculum. I have dropped a coin and it has landed on its side, which was like the most craziest thing in the most like craziest way. I was like, I remember the time 2007th grade, and like I was like in class and I was playing with the Sacagawea coin. So I had a little bit of extra. Like if you look at the Sacagawea dollar coins, it's a little fatter on the bottom, and it dropped through my desk and hit the ground like on tile, and it was spinning around like just like right where it was, and then it slowed down. It stopped exactly on the side, and I was just like, this is amazing. Like, never happened to me since. So I know it's possible at least. Anyway, so that's kind of like my kind of like, this is what probability is, right? So the thing about probability is that I think sometimes it feels very like, it gets a mix of like mathematical, but also like mind bending, like what the heck is going on? And so we're going to talk about a little bit of that. And this is where, honestly, if you guys have questions that kind of come up, especially if you've gone through the curriculum already, these are great times to like bring these up, because this is kind of like so we can work together. And a lot of times, I might also say, yeah, I'm not quite sure about this. We'd have to look at this a little bit more. All right, so I'm going to start sharing my screen just to show you some notation and like, like mathematical sense of what probability, how we can formalize our probability. And so you guys should see my screen now, and let's see where you guys go. My Zoom window always, I feel like it's like cliche now. It's like my Zoom window is always in somewhere different. It's like a little hunt. Okay, so again, it's Robbie and everyone else. These are on that repo I shared out, or that I put all the notebooks. Should be in the probability repo. And there's a few notebooks in there and stuff like that. So just kind of be aware. All right, cool. So probability. So one quick thing is that like the reason why we're doing this stuff in mathematics is to make it formalize it. In a lot of ways, we basically allow us, like the way I like to explain this, like we could try to like understand probability in other mathematical like entities essentially, or things that we try to use mathematics in without doing math directly, but it makes it really difficult. So by being able to formalize it, it really helps understand. And one thing about probability, which is really weird, I think, that people kind of forget, is that probability is just about counting. That's essentially what we're saying. It's like, well, this is all the different cases that I've seen this happen. And this is, what's it called? The number of times I've seen it happen. So the probability is this case divided by this case. Essentially, that's all we're doing. And then when we do things, when we start combining probabilities like we'll do later on in the curriculum, you basically are counting instances, but a little less formal. So this is where we actually get into sets or sets theory. So has anyone heard of set theory before, maybe going into the curriculum before? Yeah, cool, I see some nods. So set theory, if you do this like mathematically, like say like, oh, go to math class and say what set theory is. Basically set theory is just counting. Saying like, you assign, there's number of things in sets. So a set basically is like, I like to think of it like a bucket. It's like you have a thing and it's got stuff in it. Like you have this bucket and you have stuff in it. Like you have one, like a ball, or a banana or whatever you want in there, right? And so there's also something called the empty set, which you can see here with my notation. You can probably look at this while I'm talking. Is that little, what's it, like almost like a circle with a line through it. Note that this gets super confusing when you start using a bunch of other math notation, but what you'll sometimes see it, like if you see me draw it, I'll draw it like this, right? Not to be confused with theta, not to be confused with lowercase v or phi. So be aware that like, they all look very similar, but this usually denotes from context the empty set, right? So that's what this guy is. And that means just like, it's a bucket of nothing, right? And it's kind of important to know that that is a thing on its own. It's not like, it's like, oh, we're just ignoring that. It's a thing by itself. It's the empty set. So you'll see math notation use that quite a bit, and it's an important aspect. But there's a few things we should look at. So usually we denote sets as capital letters, as you can see here with A and B. Those are both sets. And then we have a few notations around there that's kind of similar to, like, I like to say, like addition. But we have things like intersections and, what's it called? Intersections and unions, right? Which is nice is because union looks like a U, so really simple. Intersection is an upside down U, which is not as simple or easy to remember, but it's not a union. So Not too bad, right? So anyway, we can do a bunch of different math notation, but I'm going to show you the most common stuff and then kind of represent this a little bit. And you've probably seen this a little bit in the curriculum, but I'm kind of reiterating parts of it. So one thing to note is that we'll usually represent like visually, you'll see like little drawings of like Venn diagrams and like squares and stuff like that and intersections, is that usually we say like the set of all things is like this rectangle. So this is like all possible events, all possibilities, right? And then we, for example, if you were to think of like, this is like all the possible ways you can flip a coin, right? Let's say like a quarter, right? Flip a coin. Then you can say it's like, well, okay, let me take a certain set of these, right? And this right here maybe represents, it's going to be like about half, right? Is like all representing all the time, or all the different ways it can land on heads or something like that. So maybe it flips different times or whatever. Basically, these are the ways it can land. He's like, okay, heads. So this would be like heads, and then like maybe something like, this is heads. The rest of this would be like tails, right? Because that's the only other possibility. And maybe I'll have like a little one that's like by itself, like on its side. Why not, right? So like you can imagine like, okay, we've got all these different like possibilities and stuff like this. So note that basically that this rectangle represents all possibilities. So it needs to be 100%, right? So basically all events will be occur there. If there's an event that can never happen, for example, I'm just making something up, right? The coin teleports out of like, you know, nowhere or whatever and lands over here. Well, that'd be an event outside of this space, right? This event cannot occur with it, given our parameters and everything. Note that we also might have, like, let's say something that's not heads and tails. We might have different event spaces where this is event A. And we might have something like event, let's try this color, event B. Okay. And so these are basically two different types of events going forward. So if basically A and B here are two different sets, they might have some similar elements. That's where this crossover comes here. They also have some elements that never occur between the two. Okay. So in this case, we would write things like, you know, let's say A with the intersection of B, right? Well, that's what this is right here. That is the intersection. So there are some points in here. So you can see here, I put a little quick thing right here. It's like, well, if the intersection of A and B is the empty set, well, that means they don't intersect at all. So if I were to redraw this a little bit, and I drew this guy, okay, that would be something that would fulfill something like this. A intersection of B is just an empty set. So there's no intersection, right? They're completely separate from each other. So what's nice is that we can actually, the probability of landing within the union of A and B is just simply saying the probability of landing in A plus the probability of landing in B, okay? So imagine if you threw like a dart on this, whatever, like going through. So there's a probability of me landing on A and there's a probability of me landing in B. The probability of me landing A or B, that union, right? It's just gonna be me just landing on the probability plus the other probability. Make sense? Cool. All right. So let's see here. One thing to kind of note is like our union here is just this guy here. So if we actually want to have a union, right? And the union between these two, if I were to like draw this out into its own separate part, it would look something just like this, just with no labels. Okay. And you can see here, that's basically the probability of A, right? Plus the probability of B minus the intersection. Well, intersection is 0, so there's nothing there. If, however, like I had in my earlier drawing, if I had B actually intersect over like this, right? Well, the union, like as you guys probably can guess, the union looks something like this. It's not a great drawing. That's something along like that, right? So that's A and B, not to scale. But the point is that this is the union here. And what this is essentially saying is like, well, okay, you take the probability of A, the probability of B, but then you subtract off that intersection part. Okay, because basically you're trying not to double count that. And so that's what this notation is really trying to show you here. It's like when you pick a union there, this is always true. It doesn't matter if they're intersecting or not. It's just that if they are if they're not intersecting, this would be 0. So it's just P A plus PB. All right, so this is kind of like notation that you'll see commonly going through like unions and what's it called, intersections and these probabilities. Note that that's what this, when we have this P of A, usually we can say the probability of A happening. That's the way we kind of phrase that, okay? Or the probability of B, or the probability of A and B. So for example, this would be probability of A and B happening. So like right here is probability of A and B happening, versus something that's probability of A or B. If it lands here or here, that would be in our set. Okay, cool. Everyone got me on that little picture and like drawing it? Cool. So I drew these parts out because this time you probably won't see this too much in the curriculum, but you might see this later on in other fields, is that this is also set notation. So for example, I just put down low text message volume day. So let's say E is the actual set, is equal to, and then note there's this little curly brace, right? So these little curly braces are representing a set. And this is reading off. I'm going to read it off to kind of go through, but some quick notation is that this guy right here, does anyone know what this Z represents? This fancy Z.
Is that like a whole set, like data set? Or?
It is a set. It's actually, mathematically, it's the set of all integers. So -1, -2, 1, 2, 0, right? So those are the set of all integers. So you'll often see this like when it's referenced in mathematics and stuff like that, but you might read this in a paper, for example. So this is important to kind of realize. There's also this R right here. That's kind of like fancy R, okay? This is the set of all real numbers, okay? So like you can think of all real numbers as basically 0, 1, 1.3, 1/3, you know, minus 293, whatever you want, right? The square root of 2, those are all real numbers, okay? Another one you might have is imaginary numbers. This is sometimes comes up, it comes up in like mathematical parts. Again, something with the square root of -1. And then complex numbers is a combination of the reals plus the imaginaries. So you'll see it like kind of like this C. Okay, so these are relatively easy. Real, imaginary, complex numbers. Okay, those are the different, if you see those like have fanciness right here. The Z is something that you'll see commonly. There's also one called the natural numbers. Does anyone know what the natural numbers are? It's the stuff you learned in grade school. 0, 1, 2, 3, 4, 5, all the way through infinity. So those are like the natural numbers. So again, these are all sets, right? There's also the rational numbers. I don't know if anyone's mathematically knows what the rational numbers are. No, okay. So rational numbers are basically numbers that can be written as a fraction. So any number that you can write as a fraction is a rational number. So for example, the square root of 2 is not a rational number because we can't write it as a fraction. 1 point, you know, I'm trying to think of a good number, but I can't. Pi would also not be a rational number. Any number that basically can be written as a fraction will be a rational number, including negatives, okay? Cool. So you can see these are all the different sets. These are the most common, like these are the common ones that you'll see in the sense of like, you know, being referred to. The ones that you probably see the most often will be the natural numbers, the integers, the reals, and then maybe you might see something about rationals, okay? Cool. So I just wanted to put that out there before you read this whole thing. And this is something that you'll see a lot of. So this next part, this little fancy E here, does anyone know how you would read this or what this is trying to tell you? It's actually in connection with this X.
Isn't it like within? So like X within.
Yeah, it definitely is like, I want to make a little caveat to that because it's not necessarily like a subset, which is different. It's like a smaller set of set, but it is like within. It usually we say like it's an element of. So it's like one thing in that set. And the way you say this is like X in Z, or like, sorry, X in the set of integers, or X is an element of the integers, or if there's some other set here, it'd be X is an element of this set. So this is that notation in there. And just know if I'll be a little careful with my wording because I don't want to say something else. Because within could also mean like, oh, it's a subset, but that would not be an element, right? An element would be like, it's an actual one individual part. I just want to make that clear. Okay, cool. So actually reading this thing, right? Let's go through it. So the way you read this is like E is equal to the set of X, and then this bar here is such that X is an element of integers such that 0 is less than or equal to X, which is less than or equal to 20. So basically what this is saying is that X is an integer, so 0, like -1, -2, you know, 0, 1, 2, 3, but has to fall within 0 to 20. Okay, an x is an element of, sorry, and this is what this x is saying. Oh, these are just the x's. And that's where this bar right here is saying such that, like basically it's a condition saying it needs to fall within this part. So you can think of this set E, it's just the numbers 0, 1, 2, 3, 4, all the way through 20. Okay. Does that make sense to everyone? All right. And just to reread this again, x is an, E is equal to the set of x such that x is an element of the integer set of integers where 0 is less than or equal to x and x is less than or equal to 20. Okay, cool. All right, and then this next one, you can just see another set. I don't know why I put this here, but I might have copied this from something. I can't quite remember. But E is equal to the set. Is this in the curriculum?
It's in the curriculum.
Okay, that's why. Okay, it's been a while since I've done this, so that's why I think I can't quite remember. All right, so this right here is reading as like x is an element, E is equal to the set of x such that x is an element of the real numbers where x is greater than or equal to 6. So basically it's like 6, 6.2, 6.1, 2 pi, 2 times pi. Those would all be elements within this set. Okay. I wanted to show you guys some mathematical notation before we go into anything else. Any questions on that? Okay, cool. Nice. So I'll go ahead and move on then. I just wanted to show you guys that, and I wanted to spend some extra time to make sure everyone understood like how to read these parts. Okay, so let's go into the actual probability now. So like I said, it's just counting. I like to say probability is just counting, but counting is really hard, which makes probability kind of hard. I think that's pretty true. It comes across really a lot. This is a subtle law that you don't have to like memorize or like, like have to like really internalize, but I kind of want to put this out, is that probability is kind of under an assumption that if we were to do this many, many times, that we would reach some truth, right? Of like, probability. So basically the probability of an event is equal to the limit of n goes to infinity of the set of n divided by n. So S of n could be just like, a positive success, right? So the success for that given n, and then divided by n is saying how many events. So the idea here is like if we were to do this an infinite number of times, if we were to flip a coin, for example, if I flip a coin 2 times and I get 2 heads, does that mean that that coin only lands on heads? Maybe, probably not, right? So it's like, it's possible, but probably not. So we have to flip it more, right? If I flip it like 3 times or 4 times or 5 times or 1,000 times or 10,000 times, if I flip it 10 million times, right? And I get all heads, can I say that that coin definitely lands on heads every single time? Yeah, I see some head shakes, also a little bit like reluctance, right? Is that like technically no, you can't say for sure, right? Because maybe you just got super, super lucky, like ridiculously lucky, right? Someone's like looking out for like you going out here, but like it just got really lucky. But maybe the next time, the millionth in like the 10 millionth in one time, you flip it and it's a tails. And that's the point what this is saying, is that we only are good at technically our probability is defined if we take it to infinity, but all we can do is estimate. In reality, usually estimates are good enough. If you flip a coin 10 million times and you get heads each time, it's probably an unfair coin. There's a pretty high chance that, it's not going to land on tails ever. But we also always consider that this is taking it to infinity. So I like to point this part out. Okay, cool. So let's actually get to some more interesting stuff, right? Versus the notation and everything. So conditional probability, just note that basically our sample space, which is kind of like a set, it's a thing of all possible events, right? So if we roll a die, for example, all possible events are either 1, 2, 3, 4, 5, 6, 7, or sorry, not 7. 1, 2, 3, 4, 5, 6, right? So all possible events. It's pretty simple, right? And next we have is independence, right? So there we go. Okay. So independent and dependent variables. So you'll hear this independence a lot. And so we actually define formally that something is independent is that basically, well, I will say informally, then we'll look at it formally, is if we say some 2 events are independent, it means that one event does not affect the other. Me flipping a coin won't affect me rolling a die. If I roll a die and it lands on 6, it doesn't mean suddenly I have a different probability of landing heads or tails. Okay, so that's kind of the idea of independent. That's also true is that we also say things like flipping the coin multiple times. every time I flip the coin, it's not going to have a dependence of what I flipped before. This is kind of like the gambler's fallacy. Have you guys heard this, the gambler's fallacy before? Can see some nods. So gambler's fallacy, just to iterate, if you guys haven't heard, is basically is that if you're betting on whether the coin's going to land on tails and it keeps landing heads, 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 but you know it's 50-50 and lands on heads, you're like, okay, land on heads 5 times. It's about to land on tails. I know it. That's not true. Every time you flip the coin, it's an independent event. So it can just as easily land on heads on the next time, you know, and the next time, the next time. That's the gambler's fallacy, where they think that the next thing's like due for something. So this is basically coming from the fact that it's independent. Let me ask you guys, are flipping coins independent? As you flip, like if I flip a coin and it lands on a certain value and I flip it again, is that going to be independent from each other? I see some nods, yeah.
I want to say in theory, yes, but doesn't it depend on like if you're flipping it by hand? Eventually your hand's going to get tired.
Yeah, you see, so there's other factors in there, right? So good, you caught exactly what I'm saying. Like in theory, in practice, it probably is independent, but in reality, it's like, well, you have to think about like, well, your hand gets tired. What if, you know, like one thing I like to joke around is like if it lands on heads, it's going to bend it slightly, you know, like maybe the coin's a little more fragile and maybe it's going to gear towards a direction. If it lands on heads more than 3 times, it's going to start going in a certain direction, then it's going to land on different parts. So like you can like make up these whole bunch of scenarios, but in reality, right, like, so in reality there's essentially nothing is independent, which is kind of a funny thing to think about. But just know that we kind of assume a lot of things. For example, one is maybe not flipping the coin 1 million times, your hand might not get tired. The coin's probably not going to bend very much, if anything, but there are things you have to kind of consider. One quick thing I will say about, I remember this paper had come out about Stanford had made a group in Stanford made a coin flipping machine, and they could actually perfectly flip the coin to land on like the exact heads or tails each time. So I don't know, it kind of says, you can actually make it deterministic, right? So anyway, cool. Oh, I see a little message. Did someone have to leave? Okay, sorry, we had to head out. Okay, so just real quick, dependent then and dependent variables. So this is a nice little graphic from the curriculum itself. I like to put this in here, is that basically like we showed before, the union is essentially the probability of A plus B, but then subtracting out the intersection, right? And that will give us, if they're independent, if they're disjoint from each other, which we'll talk about in a second, if they're completely separated, we don't need to worry about this extra part, okay? Now note that this is the definition of independent. If I mean specific, the intersection of A and B is just equal to the probability of A times the probability of B. So the intersection PA and PB is just multiplied each part. Okay. What this is saying is that like if the probability of like, let's say getting heads and then getting the number 5 on my die, right? And I roll a die and I flip a coin. To find the probability of me getting 5 in heads, all I have to do is find the probability of head or getting heads for the coin and the probability of getting 5 on a die. If they were connected in some way, it would change. I would have to consider, well, what if I get a 5 and suddenly my coin changes and the way it flips and stuff like this. So this wouldn't be as simple as being the probability of A times probability of B. That's what this is saying, essentially. Like the intersection has to be that these two are independent from each other. Okay. The other part of this too that's required is that the union, this is kind of, to be honest, this is a little bit of like just restating the definition, is that the union is P of A plus P of B minus P of A union B. Technically, you know, this holds true regardless kind of deal, but it's an important thing to note is that these are parts like, you have to consider the parts that are intersected between the two. Okay, in order to union them. All right, cool. Cool, but does everyone understand from this point of view of the intersection P of A times P of B? Cool. All right. And then disjoint, like I mentioned, disjoint does not mean independent. Like it's not sufficient enough. Well, not everything that's independent is disjoint, but if things are disjoint, for example, the probability of A union B is just equal to PA plus PB, so there's no extra intersection, then we call those disjoint. Okay, so if you were to draw this graph or this little visual here, you basically would not have any crossover. Okay, I think sometimes probability seems like it's like, oh, well, duh, like I can look at this visual and I can clearly see these points, but it's a little more subtle when you don't have like the actual numbers here. So this is actually something you can measure directly if you wanted to, but it's a good reminder going through here. Okay, and then one quick note that I had for notation is probability of A given B. So this is where A, the probability of A changes depending on B. Okay, so you can think of this like the probability of seeing, I don't know, probability of seeing a skunk given that it's raining. Okay, the probability of seeing a skunk on every single day might be like, let's say 0.2, right? 20% of the time I'll see a skunk. But if it's raining now, maybe that probability does change. Maybe I'll see the skunk less often, or if probably a better example would be like if it's nighttime, right? The probability of seeing a skunk will be increased if it's nighttime. Okay, and that's what this is kind of going into. So the way to read this is probability of A given B, okay, or such that B. So say the probability of seeing a skunk such that it's dark or given it's nighttime, okay? And that's just equal to the probability of A intersecting B divided by probability of B. And this kind of comes from the fact that we can, if we were like in statistics class, we might actually try to prove this directly, but this will actually lead us into Bayes' theorem, which will be useful on actually doing naive Bayes classification and stuff like that. But this is kind of a nice precursor to see like how these relate. Okay. All right, any questions on disjoint, independence, or just as formula for probability A given B? Sound pretty good? Cool. All right. I know it's a lot of notation, right? So I try to mix in little visuals.